We'll have 5 talks, and we'll have first 3 talks all about related to this SQR-30 project. First have Valentina give us overview of the SQR-30. Go ahead, please.
Okay, thank you very much, and I'm very pleased to be here to present you this new project. First of all, a couple of slides of scientific motivation for the survey. So we all know that the quasars at Redshift 6 are extremely important probes of the Reionization Epoch, and the first quasar in this Redshift range were found in the Sloan Digital Sky survey, and here I show this famous plot from the review by Shawi, showing all the quasars that were known at the time. And the important result, one of the main results that was obtained from this sample was the evolution of the effective optical depth with Redshift that was showing this upturn that you see here at Redshift around 6 and increase also of the dispersion of the effective optical depth values that were interpreted as a signature of the end of the reionization process. In the last 5 years, we have that the number of quasars at redshift larger than 5.6 has increased by a factor of almost 5. And this was thanks to the availability of large area service both in the optical and in the near infrared. However, we had that at the same time, the number of good quality quasar spectra that were available was very small, of the order of 10 in 2018, and also very heterogeneous. So this is why we decided to propose to ESO this large program of about 250 hours of observation with the XSHOOTER spectrograph that I remind you cover the redshift range between 300 nanometer and 2.5 micron. In order to create this sample of bright quasars, of course, we need to observe the bright objects to have a good quality spectrum, observed at intermediate resolution between 8,000 and 9,000 and a relatively high signal-to-noise ratio. Here, the observations are almost completed, and here you see a summary of the spectra nicely put together by Christine Eilers, who is part of the collaboration. The plus, let's say, of this sample is that we have also ALMA and MUSE parallel programs going on for the same objects, and that the reduced data will be released to the public as soon as the observation will be completed. So XQR-30 is a quite large collaboration, including many of the people working on the subject in the world. We have people, of course, in Italy, in INAF and Scuola Normale Superiore, then the group of Fabian Walter in Max Planck in Heidelberg, George Becker in Riverside, Shawi in Arizona, Emma Ryan Weber in Swinburne, and many other people around the world. By construction, this is a multi-purpose survey. In particular, of course, we want to study the reionization process through the Lyman alpha and Lyman beta forests. And you have already heard a talk by Yongda Zhu yesterday on the dark gaps. And after me, there will be the talk by Sarah Bott, master student Sofia Campo, who are also discussing other ways to determine properties of the reionization. Then, of course, we are also studying the metal lines in the red part of the spectra, and this is a work that is an ongoing work that is led by Rebecca Davis at Swinburne University. We're going also to study the nature of the first stars and, of course, the properties of quasars themselves and their environment. And in the next slide, I will tell you a bit more about these two projects, in particular the BAL quasars also. So here the scientific aim is to find the chemical signature of massive population tree stars at Redshift 6. And to do this, we are measuring the chemical abundances of metal-poor gaseous environment, which are traced by damped Lyman alpha systems. You know these very strong systems observed in quasar spectra, which are mostly neutral, that we identified through detection of neutral oxygen in this case. So we found 15 systems at redshift larger than 4.7. identified along 11 lines of sight. So there are, in fact, more multiple systems in some line of sight. And sorry, I forgot to say that this is a work carried out by my master student Alessio Sodini in Pisa. And for this system, then we measure the chemical abundances. Here you see, for example, the carbon over oxygen for our sample, which is shown by the red points here, compared with the literature sample. In particular, the blue points are the sample of George Becker of 2012, and also we have three measurements from the sample of Pudel et al. 2018 and 2020. So you see that let's say that the literature sample is consistent. And furthermore, we have that this gray region here is showing the average and dispersion values for the very metal poor DLAs at Redshift 3 by Cook et al. So what we see is that the high Redshift values are in general agreement with the Redshift 3 abundance, although if we compute the average of the Redshift larger than 5.7 values, this is slightly larger than the lower Redshift value. Then we have also compared the abundances for the single systems with abundance prediction, in particular for peri-instability supernovae, so the supernovae that are characterizing the explosion of very massive stars. And what we find is that the abundance pattern is never consistent with a peri-instability supernova. On the other hand, for many of our systems, core collapse supernovae with parent star of population 2 and population 1 are reproducing quite well the observed abundances. So from this study, which however is still not maybe in its final stage, but the main message I don't think will change. So from the present sample, we have that the chemical abundances at Redshift 6 for these systems are in general agreement with an enrichment due to core collapse supernovae from POP2 and POP1 stars. However, what we see is that in many abundances, in fact, we see a hint of an evolution with respect to Redshift 3 abundances. A couple of slides also on the BAL quasars. This is a project led by Manuela Bischetti, who is a postdoc at the INAF Observatory in Trieste. So BAL are these very, very broad troughs observed in some of the quasar spectra, and they are tracing ionized outflows that are thrown away to very high speed from the central AGN. So you see here two examples in XQR-30 of very strong systems, and what Manuela did was to compute the fraction of strong buzz, which is 27% in XQR-30, which increases to 47% when we include the weak BALs. Then Manuela did really a tremendous job to compare our system and the fraction that we observe at high redshift with a color-matched Sloan digital sky survey sample at redshift 2-3. And what she found was that there is, in fact, an increase by a factor of 2.5 with respect to redshift 2-3. And furthermore, as you see here in these plots, also the minimum and maximum velocities of the troughs are peaking to a much larger velocity with respect to the lower redshift. So it looks like BAL quasars are more common and stronger at early epochs, and may represent a key evolutionary phase of black hole accretion at redshift 6. And so here is my summary. So XQR-30 is the survey of 30 quasars between 5.8 and 6.6, also observed with SHOOTER at the VLT. And we hope and we think that this will be really a transformational sample for the study of the reionization epoch with the quasar spectra. Of course, we are dealing with the properties of the reionization process, and you will see more in the next talks. And the two other work that are in advanced state are these studies on the signature pop-3 enrichment for which there is no evidence in our systems. And if you want to stay updated with the news on XQR-30, you can have a look at the web page, which is now in progress. And I'm happy to take questions now.
Thank you very much for a great talk. So people can start typing in questions in Slack. I'll give you a second. Let me just ask a question then. So for the BAL work, you said they're color matched. Are they also luminosity matched? Or whether this is
of course, question? Yes.
Okay.
Yeah, we can wait a few seconds for some questions. Yeah, I guess in the meantime, I can start with one. So you had that one DLA with a very high C/O shown on plot, right? Is there an explanation for that? I mean, it didn't look like any of the stellar models actually get up to those values of C/O.
Yeah, yes. So the problem here is that, of course, we don't know exactly if what we are looking at are real damped systems. Sub-DLA. And in this case, when we measure the carbon 2 over carbon 4, for example, silicon 2 over silicon 4, it looks like the system could need some ionization correction. So let's say that in almost all the cases where the abundances were a bit peculiar, in general, we could explain them with the fact that we should need some ionization correction.
Yeah, still no talks or no questions rather. Oh, here's one from Gabor. Regarding the increase of BALs, is there any evidence for color selection effects?
No, in fact, this is I mean, what Manuela was trying to test. So what she did was to really try to select the Sloan quasar in the same way, I mean, of course, in the rest wavelength, as the XQR-30 quasar. And it looks like even if, I mean, if we don't do any color selection, in fact, the increase in fraction is even larger. But doing this color selection, still we see the factor of 2.5 more BAL in the high redshift sample. So the work of Normale was really to try to avoid this bias due to the color selection, in fact.
Yeah, I guess if I could follow up, I mean, what does it mean physically that your BAL fraction is so much higher? I mean, does it mean you're seeing further down towards the accretion disk in the emission or the absorption?
The quasar.
You're breaking up.
I mean, the quasar at this redshift are in a more violent.
Okay,
can you hear me?
Yeah.
Yeah, now.
Okay. Sorry. Yeah, no. So the possible physical. Can you hear me?
Yes.
Oh, yeah. Okay. Yeah, okay. So I think that the possible physical explanation is that there is this more violent maybe phase of accretion at this high redshift that is also causing these strong outflows.
Okay, great.